Bonsoir. Donc vous êtes venu à un séminaire exceptionnel ici, pour un orateur exceptionnel aussi. Donc la plupart d'entre vous doivent connaître l'Institut Henri Poincaré, c'est la maison des mathématiques où se rencontrent les mathématiciens et les physiciens théoriciens, qui a bien voulu donc, nous prêter cet amphithéâtre. Donc l'orateur est David Mackay, et à vous voir, je pense que la plupart d'entre vous ont dû déjà avoir le livre entre les mains. David Mackay donc, est professeur au département de physique de l'université de Cambridge, UK bien sûr. Et il a donc deux fonctions. L'autre fonction, c'est qu'il est Chief Scientific Advisor au département d'énergie et du changement climatique auprès du gouvernement anglais. Je vais lui laisser la parole. Vous avez compris que la conférence serait en anglais. Vous pouvez poser des questions de compréhension éventuellement au cours de son exposé. Évidemment, les discussions seront pour la fin de l'exposé, s'il vous plaît. Et si vous avez... Enfin, vous pouvez poser vos questions en anglais. S'il y a un problème et que vous préfériez parler français, on pourra traduire votre question. Et seuls le français et l'anglais sont autorisés. David, thank you so much.
Thank you very much. Thank you. Thank you all for coming. I think it is likely that I will say things that you don't all understand. So as Gerard said, I would like to encourage you to interrupt and to ask questions to make sure that I am clear in what I speak. In the style of a cinema, I would like to precede my main talk by a short entertainment. I am a physicist, and physicists love back-of-envelope calculations. So we take an envelope, and on the back we write down numbers, and I want to give you an example of a back-of-envelope calculation. I was having a meal with two colleagues from Shell, the oil company, and one of them said, if we grew the biofuels on the verge of the road, at the edge of the road, how wide would the verge of the road need to be to power all the cars on the road? And this is a nice example of a back-of-envelope calculation. We write down some numbers. So let's say we've got some vehicles, and let's say that their speed is 100 kilometers per hour. And let's say the efficiency of those vehicles is 8 liters per 100 kilometers, which is the average efficiency of European cars today. And then we need to look up the productivity of biofuel plantations. So that's 1,200 liters of biodiesel per hectare per year. And then we need a spacing between the cars. And let's say they're spaced 80 meters apart. We don't need to specify the length of the road, because the longer the road is, the more cars there will be, and the longer the plantation will be. So the length of the road is not relevant. What do we do with these four numbers? Well, we take the first two numbers and we multiply them by each other, and we divide by the other two numbers, and we get the answer. And the answer is that the width of the biofuel plantation would need to be 7 kilometers wide. And I like this sort of calculation, because even though it depends on assumptions which are questionable, all of these assumptions are a little bit arbitrary, we get an answer which is a very strong answer, 7 kilometers wide, and it is enough to make you say, maybe there is an issue with biofuels. So I like simple calculations like this, because you can reveal issues and interesting questions very readily. That's the end of my short feature. Now we can move to the main film. So, I'm here because I wrote a book. Please excuse the gratuitous advertisement. I wrote this book in English. I wrote it because I wanted to help people understand back-of-envelope calculations and how they apply to energy. I was frustrated and irritated with the discussion of energy in the media, I felt that people were being misled, that often people would exaggerate. I felt people were not using enough numbers. So I wrote this book and I gave it away free online. And I'm delighted that a community of volunteers has taken that free online book, which is also available on paper from our real publishers. Volunteers have taken that work and have translated it into other languages. And I'm here tonight to celebrate the launch of the French version of this book, which you can see on the screen. It's available from bookshops, you can buy it on paper, but it is also available free online. And I'm very grateful to Mise, which is the organization that has done this translation. So thank you very much. And I'd now like to tell you what the message is, or what some of the key messages of this book are. We have an addiction to fossil fuels, and it is not sustainable. When I say we have an addiction to fossil fuels, I am talking about easily accessible fossil fuels, which power most of the world today. This use of fossil fuels is not sustainable for three reasons. First, easily accessible fossil fuels, cheap fossil fuels, are a finite resource, and at some point in the future, that resource will be exhausted, and humanity will have to do something else. Secondly, climate change, which is largely caused by burning of fossil fuels, is a major issue. And third, even if there are lots of fossil fuels, it may be that your country doesn't have very much fossil fuels, and maybe you are uncomfortable about depending on other countries in the future. So those are three motivations for being interested in life after fossil fuels. And this book is intended to be a guide to help people understand the options for life beyond the current way that we use fossil fuels. And I'd like to say just a few more words about the second motivation, the climate change motivation. So, carbon dioxide concentrations have been going up. I like data, and my book has quite a lot of data in it. And when I look at a graph like this, I think, yes, maybe something did happen. Maybe humans can have an effect. In fact, I think we can say when something happened. I think we can safely say that 1769 was an important year, and maybe it wasn't just humans in general, but maybe we can identify particular humans. For example, James Watt, who in 1769 patented his steam engine, which was a more efficient way of turning coal into work. And that was one of the inventions that really helped get the Industrial Revolution going. So these measurements, which are from ice cores in Antarctica, show the signature of the start of the Industrial Revolution. Now, climate science is very complicated, and its predictions are uncertain, but the clear advice from climate science is that we need to reverse the trend of the last 100 years, and we need to stop increasing the use of fossil fuels and reduce the emissions of CO2. And there are uncertainties, but as a ballpark figure, if you want to keep the chance of a 2-degree warming below 50%, then the emissions per capita need to be below 2 tons per year per person, and ideally below 1 ton per year per person. Whereas today the emissions globally are about 5 or 6 tons per person per year. Now, we are not all equal, and some countries are different from average. So it's important maybe to look at emissions not just in terms of the global average, which is 5 or 6 tons per year per person, but to look country by country. Because some people say, oh, it's all about China. China is out of control. Well, yes, here's China. This is a graph in which the width is the population and the height is the per capita emissions. The area of the rectangle is the total emissions, and the height is the per capita emissions. So China, in the year 2000, was out of control because their emissions were about half of ours. We are over here in Europe, here's France, here's the UK. Our emissions are twice as big per capita. So I think it is a bit strange to point at China and say they are out of control. We emit far more per person, and we have been doing so for a long time. And America and Australia emit twice as much as Europeans per capita. So that's a little bit about the detail. And just to remind you, the targets I mentioned of 1 ton per year per person, or maybe 2 tons per year per person, those are shown by this green line. This is 2 tons per year per person, and the black line is 1 ton per year per person. So you can see that the standard that the climate scientists are recommending for the year 2050, which is what I was mentioning earlier, their standard of 1 ton per year per person is the standard that is currently met by the DRC, Congo, and by Bangladesh. So that's important to bear in mind. Now, where do the emissions come from? It's mainly from energy. There are other causes of emissions also, but energy is one of the big drivers. Here is a graph of energy consumption on the horizontal axis per person, and on the vertical axis we have emissions per person. And you can see a strong correlation there with a few interesting exceptions. For example, Iceland, which has a lot of renewables, hydroelectricity and geothermal. Sweden has lots of hydroelectricity and it has nuclear power. And then France is a little bit of an exception here because it has nuclear power. But it is only about 20% smaller in its per capita emissions than countries like Germany and the UK, because nuclear power is not everything. Nuclear power does not power industry, it doesn't power heating and transport. So yes, France is an exception, but only by 20% or so. Okay, and where do we want everyone to get to? If we want to achieve this target of 1 ton per year per person, we want to politely ask all of these countries to come and join the other countries that are in this box, which, as I said a moment ago, are places like Congo and Bangladesh. Yes, Gerard.
Do these figures are local consumption, or do they include the imports?
Okay, the question is, are these just local energy consumption, or do they include imports? So these numbers describe the energy consumption by the industries and activities within each country. If a particular country imports a lot of products from another country which are energy intensive, that is not reflected in their total. So for example, Iceland has this amazingly large per capita consumption. But the explanation of that is Iceland makes a very large amount of aluminium. Iceland exports aluminium to the rest of the world. So it's not the case that the people in Iceland are all living like Americans or Australians. No, they have an energy-intensive industry. Okay, in response to these motivations, people have emotional responses, and I think emotions are important. But I do think that numbers are important as well. So when I wrote the book, I tried to write a calm, factual book that everyone could agree with, and I'm delighted that the English publication of this book received endorsements from every major political party in Britain. It received endorsements from members of the Green Party and from the Friends of the Earth and from people in the oil industry and the nuclear industry. So it has achieved that goal of being a factual book that adds to the emotions by helping with some facts and some numbers. And I would like to now give you a little flavor of this guide to sustainable energy. One of the goals of my book was to try and make the numbers accessible. I wanted people to understand the numbers and to be able to remember the numbers. And if we have a description of energy in which we talk about millions or billions or milliards, or I think many people have difficulty distinguishing between 1,000, a million, and a billion, even though those numbers are very different from each other. So I went for an approach in the book where all of the numbers come in ones, tens, and occasionally 100s, because I think that's more memorable. And it's very important to do all of the calculations in the same units so that we can make comparisons. People often pick the units to try and make something sound very important and impressive. But in the book, I just use one set of units for everything. Every form of supply and every form of demand. And in the book, my choice was to measure energy in kilowatt hours, because this is what the electricity meter in your home reads. And when I get my gas bill for my gas consumption, that is also converted to kilowatt hours. And everyday activities for a single person do involve small numbers of kilowatt hours. Let me give you some examples. If you take a standard light bulb and if you leave it on for 24 hours, then that 40-watt light bulb uses 1 kilowatt hour of energy. If you eat food, then the chemical energy in the food that you eat is about 3 kilowatt hours each day. If you take one hot bath, that uses about 5 kilowatt hours of energy in the form of heat. If you take a litre of petrol and you set fire to it, that dissipates 10 kilowatt hours of chemical energy. And if you have a Coke habit, if you drink lots of Coke and you throw the cans away, the energy required to make the aluminium in the can, possibly in Iceland, the energy required to make one can is about 2/3 of a kilowatt hour. So those are examples of everyday activities that use small numbers of kilowatt hours. And I will measure power, which is how fast we use energy, in kilowatt hours per day. Now, the physicists and the engineers in the audience may at this point spit because the kilowatt hour per day is an ugly unit, and physicists and engineers have a unit called the watt or the kilowatt, which we could use as a measure of power. But there are two reasons why I use kilowatt hours per day. First, most people don't understand what a watt means or what a kilowatt means. If I were to tell ordinary people, your lifestyle requires about 5 kilowatts, they would probably say, is that 5 kilowatts per day or per year? Because they don't understand that the watt has got the per time built into it. So I use kilowatt hours per day because it makes explicit that it is a rate of using energy. Second, the watt is too small, the kilowatt is too big. All the numbers are bigger by a factor of 40 than if we use kilowatt hours per day. And so it's a more human-sized unit. Okay, let me give you a few more examples. If you drive a car 100 kilometers every day, then you are using about 80 kilowatt hours per day to run that car, if it's an average European car. If you have a typical house in North America or Europe, you might be using about 80 kilowatt hours per day to run the house. That's the heating of the house and the devices in the house. If you fly, for example, from Europe to Los Angeles and back, and if you do that once per year, on the day when you fly, you use a very large number of kilowatt hours. But if you average that number over the whole year, and you say, I have a one flight per year, a one round trip per year, on average, that habit is like 26 kilowatt hours per day. So it's like having 26 light bulbs on all the time. And finally, let's talk about another form of consumption which some people emphasize. I hope you feel a little bit scared. This was included by many people in the UK. For example, the Mayor of London said, of the 7 things you can do to make a difference, one is unplug your phone charger when you are not using it. And the text there in white says, if every London household unplugged their mobile phone chargers when not in use, we could save 31,000 tons of CO2 and £8 million per year. Wow, thousands of tons, millions of pounds. But the population of London is 7 million people, so if we divide by 7 million, it's about £1 per person per year is the saving. So maybe this isn't quite so important. Let's check. Let's do the numbers. So, is the phone charger an evil planet-destroying entity? Let's do the numbers. If you switch off the phone charger for a whole day instead of leaving it plugged in, how much energy do you save? Well, the energy that you save is on the left, and it is exactly equal to the energy used by driving an average car for 1 second. Both of those are equal to 0.01 kilowatt hours. I'm not saying don't switch off the phone charger. Do switch off the phone charger. Yes, you will save that much. But please be aware of how small it is compared to other forms of consumption in your life. And just to show it to you graphically, here are the 4 things I just described. So that each of these objects is proportional to the energy consumption. Okay. In total, The UK's energy consumption is about 125 kilowatt hours per day per person, which you can think of as roughly 40 light bulbs worth for transport, roughly 40 for heating, and roughly 40 for making electricity. The actual electricity delivered in the UK is about 17 light bulbs per person. So electricity uses about a third of the energy to make it, and in delivered form it's about 17 kilowatt hours a day per person. And as I said at the introduction, most of this energy comes from fossil fuels. This is true of most of the developed world. Most of the energy that we consume today comes from fossil fuels. In the UK, it's about 90% of our energy is coming from fossil fuels. Now, when we imagine life after fossil fuels, it's important to bear in mind another thing, which is land area. Because one of the options for life after fossil fuels is renewable energy. And all forms of renewable energy require land area or sea area. And so we need to talk about population densities and land areas. And the unit I will use to measure population density is going to be the number of people per square kilometre. In the UK we have 250 people per square kilometre, and the area per person is therefore about 4,000 square metres. If you want to visualise that and remember it, it is half of a football field. And we also need to talk about power per unit area. And I'll measure the power per unit area in the standard physicists and engineers unit, namely the watt per square metre. Okay, now let's use these units to describe the whole world. And I'm going to show you another map of the world. This is going to be a map of the world in which the horizontal axis is the population density and the vertical axis is the energy consumption per person in kilowatt hours per day. And the size of each country is going to be proportional to its land area. So I've started with the UK there, and now in blue here are European countries. And the vertical lines here show factors of 10. Both of these scales are logarithmic. So as you go from this line to this line to this line, each of those steps is a factor of 10 increase in population density, and vertically as well. It goes from 10 to 100 kilowatt hours per day per person. So I'm using logarithmic scales because it makes the map clearer. So in blue we have European countries. In red, Asia. In green, Middle East and North Africa. In blue, Sub-Saharan Africa. In black, South American countries. In magenta, Central America and Mexico. And then in a bukey green colour we have Canada, USA, Australia and New Zealand. So there is the map of the world. And one striking fact you can see here is that there is a lot of variety in the world. The population density varies by more than a factor of 100 between countries, and the energy consumption per person also varies by a factor of nearly 100. So top left we have Iceland, Canada, Australia, with very low population densities and very high per capita consumptions, 300 light bulbs per person. Top right, Bahrain has the same energy consumption per person as Iceland, and its population density is about 300 times greater. Bottom right, Bangladesh consumes about 100 times less per person than Bahrain, but it has the same extremely high population density. And then bottom left, well, there's no one there, but there used to be countries there, because actually everyone is moving to the right and up. Most countries are moving to the right and up. Let me show you that with these little vectors, these little blue tails. So behind China, we have 15 years of progress. Here's 15 years of progress for Portugal, for Brazil, for Algeria, for Sudan, for Libya, and so on. Many countries are moving to the right and up. So they're coming to join us in the top right-hand corner, us being UK, Germany, Japan, and France has a lower population density by, well, that's a factor of 2. So you have half the population density of the UK. So the answers depend on the country. Some countries have different answers for their energy future from others. But maybe Germany, Japan, and the UK are typical of where many countries are going to be in the future. They are above average, but actually most countries are already above average, and most countries are heading up in that direction. When I say most countries are above average, let me be precise. The world average power consumption is 0.1 watts per square meter, and that's shown by this line here. If you multiply the energy consumption per person by the population density of a country, you get the power per unit area of that country, which we can measure in watts per square meter. So all the countries on this pink line here have the same power per unit area as each other. 0.1 watts per square meter is the power per unit area of Saudi Arabia, Norway, South Africa, Mexico, China in 1990, India in 1990, and Bangladesh in 1990. And that is also the world average power consumption. But most countries are above average. Most people are above average, is what I really meant to say. Most people live in countries that are above average, because about 80% of the world's population is above that line, above 0.1 watts per square meter. So, yes, the UK and Germany and Japan are slightly atypical because our power consumption is about 1.25 watts per square meter, but 80% of the world's population is above this line here. So this is a good and is an interesting example to look at. And if we think about Germany and the UK, which is what I might focus on now, all the answers for France are fairly similar. France has the same per capita consumption, roughly, but its population density is half. So there's a factor of 2 difference, which is a relatively small difference compared to these bigger differences here. Now, what can we do with this diagram? Well, I've shown you the power consumption today of all of these countries. We can now compare these power consumptions per unit area with the power production per unit area of renewables. So let's shrink the figure down a little bit, and we can add some more lines to show the power per unit area of renewables. First, let's start with energy crops. In my little introduction, I mentioned biofuels. And here is the number for the best energy crops in Europe. There is a range, but a typical figure is 0.5 watts per square meter. Now, that is smaller than 1.25 watts per square meter. What that means is even if you covered the whole of the UK with energy crops, the energy from those crops would not equal the energy consumption of the UK today. You would need 2.5 times the area of the UK in energy crops if you wanted to match today's consumption entirely using energy crops. Even France, with its lower population density, has the same message. If you covered the whole of France with energy crops, the output of those crops would be less than today's energy consumption in France. So that's an interesting message. Wind power can deliver more power per unit area. In the UK, wind farms deliver about 2.5 watts per square meter. In this book, I said that onshore wind farms delivered about 2 watts per square meter, and I'm happy to correct errors in my book. And that was an error. Onshore wind farms deliver a little bit more than 2 watts per square meter. They deliver about 2.5 watts per square meter, and here's the data to back up this correction. So here are about 50 wind farms in the UK. The horizontal axis shows the area of the wind farm, and the vertical axis is the actual power per unit area, the average power per unit area. And there's a great range, but they're all between 1 and about 4 or 5 watts per square meter. In my book, I said that offshore wind farms might give you about 3 watts per square meter. That was also an error. These 4 farms here are the offshore wind farms of the UK, and they're delivering a little bit less than 3 watts per square meter. So I'm always happy to correct errors, and my summary is all the wind farms are delivering roughly 2.5 watts per square meter. So what does that mean? It means that if you covered half of the UK with wind farms, the average output of those wind farms would equal the average energy consumption of the UK. That's the total energy consumption of the UK in all forms, not only the electricity, but also the industry, heating, and transport. And there's a similar message for other renewables. Next, let's talk about solar. Solar panels on a south-facing roof in the UK deliver about 20 watts per square metre. And here's some real data from a roof in Cambridge showing that you get a power that varies throughout the year, and on average it is about 20 watts per square metre. So if you were to cover all south-facing roofs with solar panels, you would get an appreciable amount of power, but not the total power consumption of the UK. If you want to get more power from solar panels, you need to leap off the roof and adopt the traditional Bavarian farming method. In Bavaria, it is traditional to cover the countryside with solar panels also. So here's a photograph of Bavaria, and the power output of these solar facilities is less than 20 watts per square metre, because 20 watts per square metre is the power output of one panel, and when you make a solar park, you have to have gaps between the panels, as you can see in the photograph. You have to have gaps for the humans to get round and clean up the panels and do maintenance, and you have gaps to prevent the panels from shading each other. And the actual power output of these farms is something like 5 watts per square metre. That's the power.
This is average over 24 hours?
Yes, this is the average over 24 hours, and it is the average over 365 days of the year. So on average, you get 5 watts per square metre from these solar parks. I don't have actual data from these Bavarian parks. I've tried to find it, but I do have actual data from an American solar park. This is one in Vermont. The intensity of sunshine in Vermont is bigger than in the UK. In the UK, the average intensity of sunshine is about 110 watts per square metre. In Vermont, it's bigger, it's 140 watts per square metre. And the power output of the wind farm is about 3.8 watts per square metre. So this is a modern, very new solar farm.
You mean it's an average day and night?
That's correct. It's an average day and night. I've taken the total energy output and I've divided it by the number of days in the period. So for each of these, I took the energy produced in 1 month and I divided it by the duration of that month. And then you divide by the land area to get the power per unit area. And I take the whole area, which I measured on Google Maps to find land area of this solar facility. So that is not very much bigger than the wind farms that we were discussing earlier. So what's the message of this? Well, if you needed to cover half of the UK wind farms to completely cover all forms of energy consumption in the UK, you only need a quarter of the UK covered with solar facilities in order to produce, on average, the total energy consumption of the UK. So that is nevertheless a large land area. Another option is concentrating solar power, which perhaps can deliver more power per unit area. Of course, you need to have deserts for this to work, and Britain doesn't have any deserts yet. And the actual power output of concentrating solar power facilities is something like 10 watts per square metre. This facility delivers 14. This one in Spain delivers 10 watts per square metre. It also has storage tanks using molten salt to store heat overnight, which is a very nice trick, because the average output is obviously much lower than the peak output, because the sun comes and goes. And by using molten salt, they can store heat from the day into the night. The average power output is 10 watts per square metre. And here's another facility in Spain using a solar tower, and this facility delivers 5 watts per square metre. So being generous, let's say concentrating solar power could deliver maybe 20 watts per square metre. That's another factor of 4 bigger than the solar parks we were talking about earlier. So instead of building solar parks in Bavaria, you could build concentrating solar parks in someone else's desert, and the size of those that you would require would be 4 times smaller than the size required in a typical northern European location. Yes, Gerald.
Not here. What do you do with the? So you concentrate heat. So what's going on there? I mean, there's a turbine. I mean,
Yes. So the question is, what's happening in one of these facilities? The sunshine is being concentrated on a very small spot at which the temperature becomes extremely high. And they put a boiler there and they generate very high temperature steam and they put that through a turbine. So that's the method used in this solar tower. Similarly here in Andersol, they're concentrating the heat onto these little pipes here, and these pipes actually contain molten salt that's going through them, and then that molten salt is used again to generate steam, to generate electricity. So electricity is the output of these facilities. In principle, you could do other things. For example, you could deliver the steam to run industrial processes, and this company here, eSolar, they are interested in not only generating electricity, but also delivering high temperature heat for industry.
Now the heliostat or fixed mirror.
These mirrors in the eSolar facility are all heliostats. They follow the sun. Similarly, these are sun following solar concentrators. They have a Stirling engine at the focus. And these troughs in Andersol tip around 1 degree of freedom. Similarly, these mirrors also track the sun in order to concentrate it on the tower at all times. Okay, so here are some renewables, and the message is, I love renewables, but all of them are quite diffuse. Some of them are even more diffuse than others. When I say diffuse, I mean that the power per unit area is quite small. Here's a table listing the power per unit area. I've talked to you about wind, bioenergy, solar photovoltaic panels, and solar in deserts. Let me just mention one other option, which is to use the tides. So there are two ways to use tide. One is to have a tidal basin, and it fills up at high tide, and then at low tide you let the water out, and it's like a small hydroelectric facility. And France has one of the longest running and biggest of these facilities in the world. It's at Lawrence. And the power per unit area of Lawrence is 2.7 watts per square meter. That's the power per unit of enclosed area. So I took the area of this region here in order to define the power per unit area. And in Britain, a possibility is that we might develop a similar facility on the Severn estuary, and these two maps show the Severn estuary and Lawrence to the same scale as each other. So there's our number, 3 watts per square meter, which is similar, again, to wind farms. So the message is, if you want a tidal basin to make a very big difference, you need a tidal basin that is the size of your country, not just the size of Lawrence estuary. And Europe is actually equipped with such a facility. The North Sea is a very large tidal pool into and out of which great flows of water pour through La Manche and through these channels here up around the Orkneys. And it's possible to use that natural tidal pool to generate a lot of energy in another way. Namely, we put a generator in La Manche or up in Orkney in order to exploit the big natural countries as that tidal pool receives and loses water. And this can be done with what we call in English tidal stream. Tidal stream means underwater windmills. So you take a windmill, you put it underwater, and we have one of these working in the UK at the moment. It's actually working in a place called Strangford Lough here in Northern Ireland. And there are a few other examples in North Korea and in Norway. So tidal stream is a very young technology, and it's quite hard to estimate what its power per unit area will be, but in my book I estimate that it might deliver something like 8 watts per square meter. It depends on the location and so forth, and maybe on details that we still don't understand. But it's in the same ballpark as all the other renewables. So what does this mean? It means that if you want in the future to live on renewables, and if you want to live at today's energy consumption, then if you are in a European country, you need to expect those facilities to have a similar size to your own country. They can be a little bit smaller, maybe about 10%, but maybe about 10%, 20%, 5% of your country would need to be occupied by renewable facilities if you want to sustain today's energy consumption on renewables alone. And this is true whatever mix of renewables you go for. As you change the mix, you might have more solar power and less wind farms. You can put them in the same location if you want. You can have energy crops in among your wind farm. If you do that, then that combined facility produces 2.5 plus 0.5, which is 3 watts per square meter. And the argument is still the same. The total area of those facilities will be quite big. Yes?
How is can the tidal power be larger than the one at Clarence or 7? You would need a higher tide height.
Okay, so the question is there an inconsistency between these two numbers for tidal power? The reason for the apparent inconsistency is my definition of the area. When I told you about the power per unit area of Clarence, I divided the power output by the enclosed area here. When I estimated the power output of a tidal stream facility, I took the area of sea occupied by the turbines. I didn't include the area of the North Sea as part of the facility. So in the location where you put the turbines, you have more power per unit area. Okay, so there are the power per unit area of some renewables. There are some other renewables, and I mentioned them in the book also. For example, wave power and geothermal power. And those forms of renewable generation have similar issues. They are diffuse. There are other ways to make low carbon energy. And one of those is nuclear. And the power per unit area of a nuclear facility is in the ballpark of 1,000 watts per square meter, which is significantly bigger than the renewables.
Does this take into account the surface for mining the uranium?
Okay, so the question is, have I included the area for mining the uranium in this calculation? And the answer is no. To get 1,000 watts per square meter, what I did was I divided the power coming out of this facility, which is Sizewell B, by the area of this square here. And Sizewell B produces 1 gigawatt on average, and the area of the square is 1 kilometer. So 1,000 watts per square meter. That's the calculation. If I included the land area for the mining of uranium also, as part of the footprint of the power station, then we would have a smaller number. So let's talk about that. The uranium for much of the world's power stations today comes from a single mine in Australia called Olympic Dam. And that mine is not solely being used for uranium production. If it were being used solely for uranium production, you could do a calculation and you could say how much electricity and what's the land area. And the answer is about 1,000 watts per square meter is the power output of Olympic Dam. If you then add those two together, you could say, the total footprint of nuclear is actually 500 watts per square meter. So you get half as much because it needed to include the mine as well. So, all right, it's 500. But do remember, Olympic Dam produces other things. Uranium is actually a co-product along with the principal products of Olympic Dam. Olympic Dam produces zinc and copper and all sorts of other things. So the uranium is almost free at that mine. I'm sure there is some additional work that has to be done there. But yeah, about 1,000 watts per square meter. Now, there are nuclear facilities that have higher power per unit area. Here's Gravelines on the north coast of France, and it has not one PWR in its square kilometre. It's actually got 6. So here are the 6 of them, and here is the square kilometre that encloses those 6 and all of their facilities. So the average power output of Gravelines is 4,400 watts per square metre. So by this metric of power per unit area, nuclear is less intrusive than renewables. Of course, this is not the only metric that we care about. We don't only care about power per unit area, and there are many other important metrics. Things like the long-term legacy of waste and cost and all of those sort of things too. So when I say nuclear requires less land than wind, I'm not saying nuclear is better, it's just some numbers. which are hopefully helpful. And when we notice that nuclear has popularity problems, we should also notice, yes, nuclear has problems, but so do renewables. This is a photograph of a consultation exercise in full swing in the little town of Pennycook, just south of Edinburgh in Scotland. And you can see the children of Pennycook celebrating the burning of the effigy of the wind farm, the windmill. So many options have popularity problems. And we need to take into account these popularity problems for nuclear, for wind, for lifestyle change, and so forth. And we need to understand the numbers, and we need a plan that adds up. And what will that look like? Well, it will depend on which country we are talking about. For countries in the top right-hand side of this diagram, which I would like to focus on, places like Germany, the UK, Japan, and France, the message is, you can live on renewables as long as they're large. You can also live on nuclear as long as people embrace it. Or a third option is you could talk very politely to countries over in the left-hand side of this diagram who have very low population densities. And you could say, we don't want renewable energy in our backyard. Please can we make renewable energy in your country instead? The size of that facility will still be roughly the same size as it would have been in your own country, maybe a little bit smaller. So you could talk politely to Libya, and to Kazakhstan, to Mongolia, and other countries like that, and ask for energy from them. And those are supply options. And there are other supply options too. And you can imagine all of those having levers. These are some of the options we can use. Our renewables, other people's renewables, nuclear, and so forth. For example, carbon capture and storage is another technology I would like to mention. That means let's carry on using fossil fuels, but let's at least capture the CO2 that we normally release, and let's bury the CO2 somewhere underground. There is another option. You don't have to continue with today's energy consumption. So a possible thing that a country like the UK or Germany could do is it could reduce its per capita consumption down to the levels of China or India, say, and that would reduce the required power so that it would be easier to deliver the power from a smaller amount of renewables, a smaller amount of nuclear, or a smaller amount of someone else's desert. So the full set of levers has some green levers, which are supply side levers, and then there are red levers, which are levers that reduce our energy consumption. And in the book, I describe how the major sectors could have their energy consumption reduced. And I focus on transport and heating, and the way that individuals can actually change their lives by understanding their energy consumption better. So I'd like to talk to you about these three red levers on the right-hand side. Obviously, there are other demand-side options as well, but I'll focus on this. So let's start with transport. How do we make transport more efficient? Well, the laws of physics say that you need to do 5 things. First, you want your vehicle to have small frontal area per person. This reduces air resistance. Second, you want your vehicle to have small weight per person. That reduces rolling resistance and it reduces the braking losses. Third, you want your vehicle to go slowly. This reduces air resistance and braking losses. Fourth, to save energy, go steadily. Don't speed up and slow down. That reduces your braking losses. And fifth, you want to convert energy efficiently between different forms. The standard vehicles we use today are only about 25% efficient at turning chemical energy into work at the wheels. And we can do much better. So when you apply all of those principles to the standard vehicle of today, which is a car with 1 person in it, which uses 80 kilowatt hours per 100 kilometers, if you apply all of those principles, what do you get? Well, you get this. It's 3 people on a bicycle, and it uses 1 kilowatt hour per 100 kilometers. Now, some people would call that a lifestyle change. And there are other options in between these extremes which use the laws of physics in various ways. So you can also travel in an eco-car if you want to have the comfort of your own car, and this eco-car is shorter than a traffic cone and it comfortably accommodates one teenager. And it has a similar energy consumption to the bicycle. It delivers those results if you travel at 15 miles per hour, which is about 23 kilometers per hour. And again, the lady who drives this tank here might say that that is a lifestyle change. So another option would be, you want to go fast, so go in a TGV. If you go in a TGV, the energy consumption is much lower because you are sharing the frontal area with a very large number of people. So you only need 3 to 6 kilowatt hours per 100 kilometers. But the lady in the tank will say, no, that's a lifestyle change. I can't travel with all those horrible people. And so she will prefer perhaps an electric car. Electric cars are much more efficient than standard cars in turning chemical energy into oomph, because their efficiency between the battery and the wheels is about 85%. Of course, you need to ask, where did the electricity come from? And if your efficiency for making electricity is only 30%, and if you're using fossil fuels, then this has not really given you a win. But if you can make the electricity from a different source, then electric vehicles may be a helpful solution. Okay, so there are some choices on the transport side. Now let's move to heating, and I'm going to focus on the heating of buildings. So a typical poor quality British house looks like this. This is my house in Cambridge. This is my Ferrari. And what can you do to this house? It leaks heat. Well, let's look at the physics. The physics says that the heat loss is proportional to the leakiness of the building multiplied by the temperature difference between the inside and the outside. And then the power required to make up for the heat loss is the heat loss divided by the efficiency of your heating system, which we call the coefficient of performance of the heating system, the efficiency with which it turns energy in one form into heat in your house. Now, how can we reduce the power required? Well, you attack the 3 terms on the right-hand side. So you can reduce the red temperature difference between the inside and the outside with an amazing technology called the thermostat. You grasp the thermostat and you rotate it to the left, and your energy consumption reduces. I have tried it, it works, and some people call it a lifestyle change. But I'd like to, I will emphasize later on that actually this is a very important technology which I think everyone could use, and it could make a big difference. I'll come back to that. Secondly, you can reduce the leakiness, the déposez. The leakiness, which is to do with leakage through windows and doors and walls and roof and floor. So in my house, I got a new front door, and I got a fluff man to come and put fluff in the walls. So he put extra insulation into the cavity in the wall, and we got loft insulation, extra loft insulation, and I think that reduced the leakiness by about 25%, from 8 kilowatt hours per day per degree to 6 kilowatt hours per degree day. So that's a 25% improvement, that's worth having. But it's not a huge transformation. Here are some more photographs of other things you can do to reduce the leakiness. So you can put extra insulation on the exterior of a building, and if you put maybe 12 centimeters of rock wool, you can bring up the building closer to modern building standards, to the standards that are normal in Sweden. Here are some photographs from this is Martin's house. Martin has put exterior insulation on the outside of his house. And here are some pictures of the clever trick of moving the windows out into the insulation so as to create a nice little step, a little bay, which is a nice feature in Martin's house. So it can be done in France as well as Germany and Poland. The third thing is we can make heat more efficiently. The standard heating system in the UK is a gas boiler, which takes natural gas and sets fire to it. And it has an efficiency of maybe 90%. And that sounds quite good. But you can actually do much better than 90% efficiency. You can use a heat pump, which is a device that uses energy from the electricity to move heat from your garden into your house. So here's some photos of an air source heat pump. And here's another air source heat pump in Japan. This one is called EcoCute. and it has two parts. It has pumpu and it has tankman. And they're both amazing. They've got gloves and a cape, and cute eyes and everything. So the efficiency of a heat pump is better than 90%. How can it be better? Well, the efficiency of EcoCute is claimed to be 490%. So you put in 1 unit of electricity, and then pumpu pumps 4.9 units of heat into tankman. So it's one of those 4.9 units comes from the electricity, and the other 3.9 units come from the air. So it's cooling down the air in order to make heat in the place where you want it. So you can do much better than 90% efficiency. So heat pumps. And in Japan, heat pumps are going up and up. Here in red is the deployment rate of heat pumps. Each of these points shows how many heat pumps were installed in 1 year. And this is just the EcoCute heat pumps. They're installing 500,000 of them a year in Japan. Here's a similar graph for France, and the number of heat pumps installed has gone up and down and up and down, and so there seem to be some problems in France. And if any of you are experts on this topic, I would be very interested to hear what has been happening in France. We have similar issues in England, where the deployment rate is even smaller for heat pumps. The third red lever I would like to mention, I call read your meters. Read your meters works like this. In this house that I mentioned earlier, I had energy meters. I had a gas meter and an electricity meter, and I never read them. And I started writing a book on energy, and a friend said to me, "How much energy do you use at home?" And I was embarrassed because I didn't know. I wasn't looking at my meter readings. I wrote them down, but I once a year maybe, and I didn't actually relate to them. And so I turned my eyeballs into a smart meter, and I started reading the meter every week, and it changed my life. And these graphs show what happened to the gas consumption. So in the past, I was using about 40 kilowatt hours per day on average, and then I started reading the meter, and the consumption was reduced to 13 kilowatt hours per day. And that came from my interaction with the meter and the thermostat, because I discovered that you don't need a particular temperature all the time. Sometimes you want 19 centigrade, but sometimes 13 centigrade is just fine. And so I started to tinker. I started to change my thermostat a lot. And whenever it could be low, I made sure it was low. So the thermostat is often at 13 centigrade in my house, and sometimes it goes up to 16. And if we feel at all cold, we put it up to 19, or to 20, or to 21. It doesn't matter, because most of the time it's at 13 or 16. And that's how you save more than half of your energy. Similarly, with electricity, I read the meter regularly, and I discovered that there were vampires in my house which I could switch off and which did make a difference. It wasn't the phone chargers, no, not the phone chargers, but computer peripherals, the cable modem, the stereo that was on all the time, the DVD player that was on all the time. And I switched all of those things off, and I found that I could get a 45 watt saving. That's 1 kilowatt hour per day, so 1% of my total energy consumption, which is well worth having, because that saves me £45 per year, and we can spend that on an extra holiday in Lanzarote. So, let me wrap up. We need a plan that adds up. To make a plan that adds up is difficult, because if we want to get off fossil fuels, today we use, the developed world gets 90% of its energy, roughly, 80% from fossil fuels. So a very big change is needed. So you need to push hard on many of these levers. And many of them are difficult levers to push on, because people don't like having wind farms in their landscape in some parts of Europe. And people aren't comfortable with asking other countries to give them their renewables. And people resist the lifestyle change. Not everyone wants to ride a bicycle or travel on a train. So it's difficult. And we need to think carefully about the numbers and make a plan that adds up. The plan has to add up not only on average, but it needs to add up at every minute of every day. And one of the things I would talk about if I had another hour would be the topic of dealing with the fluctuations of wind, the fluctuations of electricity demand, and the fluctuations of heating demand. These curves show electricity demand in the UK, fluctuating every day. These show the output of a wind fleet. I'm imagining that if the UK had a wind fleet that was 50% bigger than that of Germany, what would the output of that set of wind farms be? And this graph shows the gas demand of the UK, the heat demand, if you like, of the UK, varying throughout the year. And these are all on the same scale as each other. So there is a very big issue. If we want a plan that adds up, we need to cope with the variation in heating demand, which varies by a very large amount. In gigawatts, it's going from 200 gigawatts at peak down to 80 gigawatts in the middle of the summer, which is much bigger than any of these variations in the electricity system. So, we need a plan that adds up, and people who make opinions and people who make policies need to understand arithmetic. So that's why I wrote a book. And I'd like to finish by telling you what has happened since I became Chief Scientific Advisor to the UK Department of Energy and Climate Change. One of the projects that has happened there is called the 2050 Pathways Project, and the department has made a piece of software that implements the ideas of this book in far more detail and in a completely open source way. So again, this tool is available free online, and it allows the user to explore different possibilities for the UK on the demand side and the supply side. And the tool has not 6 levers, but 42 levers. So here are the 42 levers. The demand side levers are here, the supply side levers are here. And this tool has been replicated for China. The Chinese government has made its own version of this tool. So here's the Chinese calculator, which was published this year. And not to be left out, Belgium has a calculator. So here's the calculator for Wallonia, and here is the website for the Wallonian calculator, which is in French. And so here are the levers in the Wallonia calculator. And again, there are about 42 levers on the demand side and the supply side. So I'm delighted that these ideas are getting some traction in some governments, and I'd like to perhaps leave you with a challenge where maybe France would like to have a 2050 calculator as well. So let me finish by saying how grateful I am again to Lamid for making this free translation of my book. I'd like to encourage you to download it and to buy the paper copy as well. It's not easy to make plans that add up, but it is possible. Thank you very much for listening. There's a question in the middle there. Shall we use the microphone?
The way we do consume energy is closely related to the price of energy. Can you say, I mean, it is there, of course, when you turn regulation, it's cost naturally. But if you want to install more or less on these devices, of course, for a government, cost will be a priority.
Good, so the question is, what about prices? And in my book, I say almost nothing about prices because I wanted to write a book that was about the laws of physics and the constraints that physics and engineering place on what is possible. And the laws of physics don't change, but the prices of everything change all the time. I noticed this today because I came from Britain, where a cup of tea costs maybe £1, and here in Paris it costs about £5 a cup of tea. So prices are crazy. Nevertheless, it's a very important question. What do these things cost? If we want to make a plan that adds up, it has to add up in terms of physics, and we also need a financing plan, and we need to understand the costs of the options. And those costs are very uncertain. We don't know the future. But all of these calculators include a cost feature. So here in the Belgian calculator, we have costs. And in the British one, we have costs as well. The costs have error bars, and so you can see what pathway you want, and you can see what the costs are with error bars. And the rough message is that business as usual carrying on using fossil fuels has a big cost, because if we continue as normal, we will carry on building buildings, we will carry on making transport systems, we will carry on making power stations, and those will have a cost, and the fossil fuels have a cost too. And so the cost is probably going to rise in time and be big. So that's business as usual. The cost of any of these pathways which take successful action on reducing fossil fuel dependence and reducing climate change, it looks like this. So the cost is bigger today and smaller in the future, because all of these good ideas, building insulation, nuclear power stations, wind farms, they all cost a lot today, and then they cost nothing in the future, because insulation is free once you have made it. Nuclear power is, well, not quite free. Wind farms are nearly free in the future as well. So it's a choice between this cost, which is business as usual, and this cost if you take action. And the area under the two curves is about the same. So as long as you look at the total cost over a long time, the cost is much the same, but this pathway takes climate change action, which has a very significant cost that I did not show with my two arms.
Yes. Something which amazes me and terrifies me also is the permanence of car traffic. If you go and stand on a large bridge over any highway in the world, then you will see cars going and coming, day and night, morning and evening, non-stop. How long will it last? 100 years? 1,000 years? Mankind exists since over 100,000 years. This traffic was not necessary and possible 100 or 200 years ago, and it will probably not be possible in a couple of hundred years from now. I just wonder why people don't think about it. How long will it last? How long? Surely not as long as mankind. Could we, for the time being, imagine something like a sabbatical day a month, just to let nature recover from this non-stop culture?
Okay, so if I understand the question right, the question is about how long things last, and one way of interpreting that question would be, are the ideas in this book going to be relevant still in 50 years' time? Some people might ask, maybe in 50 years' time there will be some complete breakthrough and some change. And if that does happen, obviously everyone would be delighted, but I believe that the responsible thing to do is to have a plan based on the assumption that there is not a massive breakthrough, there is not an amazing new technology that has not been discovered. My feeling is that's the responsible thing to do. You suggested taking one day off per month to help the environment recover. That would make a difference, I suppose, of about 3% to some forms of the damage we do. And in particular, for climate change action, that would probably not be enough. Need not a 3% reduction, but a 90% reduction by 2050 is the current advice.
From what you said, it's 1%.
I'm sorry?
From what you said, it's 1%. Because transport is 1/3.
That's true. I was assuming that we would take a holiday of all forms of activity, not just transport.
Thank you very much for this very nice presentation. I think one of the issues with energy production is that quite often you produce energy when you don't need it and where you don't need it. And that means that there are two major questions, which is the storage and which is the transport. How would that enter the picture? And could you give a sort of guideline how much we would be able to improve if we were transporting more efficiently or if we were storing more efficiently?
Good. So the question is, what about fluctuations and what about transport? Because maybe the energy is created in the wrong place and at the wrong time. So I mentioned fluctuations here, and the additional infrastructure required to store energy could be extremely large. And so storage is a very big challenge. In the UK, we have a storage facility that looks like this. It's a pumped storage facility. You probably have some of these in the Alps also. This facility is made of 2 lakes on a mountain. So here's the upper lake and here's the lower lake. And the total energy stored in this facility, where water is pumped up the hill when we have an excess of electricity, and then it is let down the hill when we want to generate. The energy stored is about 10 gigawatt hours. You could compare that with the amount of energy you would need to store if you wanted to store 5 days of no wind. So if we go back to this graph here, which shows the wind production from a fictional collection of wind farms. From time to time, there are periods with no wind at all, or almost no wind. On average, the output of these wind farms is about 10 gigawatts, but sometimes there is no power. So how much energy do we need if we want to cope without 10 gigawatts for 5 days? The answer is 1,000 gigawatt hours. So you would need 100 of these facilities if you wanted to do it with pumped storage. So storage is very difficult, and I think it's a very good idea to have innovation support and research and development into new technologies for storage. One possible way of doing this is to store heat underneath buildings. So this is a very simple idea. You can use, this is a building where the playground is being used as a collector for sunshine, and that heat is being pumped under the building. Then in the winter, the heat is pumped back out. This doesn't solve the electricity storage problem, but it is an idea that could be part of a solution. Here is a community using the same idea in Canada. They have solar hot water panels, and they store heat down in a big hole in the ground that is 30 meters wide and 30 meters deep. Again, this doesn't solve the electricity balancing problem, but it does help with the other fluctuations problem, which is here. This is the heating problem, which is an even bigger problem in the winter than this problem of the wind. So we need a solution to the heat problem too. And then there is another technology which I'm excited about, which a company called Isentropic is developing. And that is here. So this is a heat pump which is very, very efficient. It is nearly reversible. It can be used to pump heat from one place to another, and in the other direction you can take the heat back and generate electricity. And the idea of Isentropic is that they could replace a pumped storage facility, which is this big. Here are 2 very big lakes. They could replace that facility with 2 relatively small buildings, which would be able to store 30 gigawatt hours of electricity in the form of heat, using this reversible heat pump. So this is a British company with another idea of how to do storage in perhaps a smaller and less expensive way. You also asked about transporting energy from one place to another. So if we were to generate energy in the Libyan desert or somewhere in the Sahara, can we transport it to France or to the UK? And what are the losses there? The energy losses would be relatively small. You would lose probably about 10% of the energy in transporting it from the Sahara to the UK or France. The other thing you would lose, though, is you would lose some land area, because you would have power lines going all the way across Spain and France for the benefit of the UK, and the area lost would be quite substantial. It would be similar in size to the area of the concentrating solar power station. Not quite as big, but there would be a land requirement for the additional power lines. Alternatively, you could bury the power lines, and that might be more acceptable, but it would be more expensive. So there are always trade-offs between land area and location and money.
Yeah, I have a similar question as storage, but until storage is solved, isn't it true that intermittency at the moment implies that renewables have, as a consequence, more fossil fuel consumption than before?
Okay, so the question is, do fossil fuels increase, do renewables increase fossil fuel consumption?
Yeah.
So for example, in Germany, the amount of wind they have is not quite as big as this graph. They have about 23 gigawatts of capacity. This is the graph for 33 gigawatts. And so the fluctuations of wind output are essentially negative demand on the electricity system. So instead of having this simple electricity demand, they have a random demand that is smaller. What are the consequences? Well, the total energy required from fossil fuels is smaller because the average has gone down by quite a lot. But the efficiency of those power stations will be a little bit worse because they are having to cope with a less simple, a less predictable demand. I think the effect is small though. I think it is in the ballpark of a few percent change in efficiency. So I don't think it's correct to say that the overall effect is an increase in fossil fuel use. I think there is a saving. It's quite a big saving, but it's about 3% less than the saving you would get from a simple calculation. I've got a team working on that question in my department at the moment to try and get a better answer to it. We will publish that work hopefully within the next year. So yes, renewables today do create fluctuations. The solar facilities in Germany also create a fluctuating supply, but that is more predictable. It tends to peak at midday, and midday in Germany is the time of peak electricity demand. So there is a reasonable correlation there between the normal fluctuations in demand. In Germany, their peak is at midday. However, in the UK,
No? Are you sure it's midday? It's not 7 p.m.?
in the UK, our peak is at about 7 p.m. So there seems to be a difference in lifestyle between Germany and the UK.
France, it's 8 p.m.
Okay.
No, France is the peak. There are two peaks in France, one in the morning and one in
So,
due to electricity.
So people have different lifestyles, and in France there are two peaks, and I think in France everything is much more regular, so all the peaks and troughs are bigger because everyone has lunch at exactly the same time, whereas in UK you can't detect a lunchtime peak.
You have tea time.
Yeah, we have tea time, but again, we are not so regular about our tea time. It can move between 3 o'clock and 5 o'clock.
In your book, you speak quite a lot about stuff, or what you call stuff, and the problems of producing all of it and transporting it. Do you still see potential for energy savings in that area?
Yes, that's a nice question. So the question is, what about stuff, the things that we buy and throw away? I didn't mention it in my talk, but stuff is a very big part of our footprint because a lot of industry is making stuff for us, which we then throw away, and quite a lot of the transport is transporting stuff around. And much of that making of stuff happens in other countries, and so we are not so aware of the energy footprint. But in my book, I estimate that maybe as much as 50% of our footprint corresponds to stuff being made by other countries for us. So I said our energy consumption is about 125 kilowatt hours per day per person, but maybe there's another 100 kilowatt hours per day per person in other people's countries. So yes, stuff is enormously significant, and if we reduce the amount of stuff that we use, or if we make that stuff last for longer, which is just as good, that could have a very big effect on global energy consumption.
A question about the difficulty to explain these facts and the physical laws to citizens, and in particular to politicians. Have you got some plans in UK to do that?
Okay, so the question is, how do we explain difficult ideas from physics to politicians and to other people who matter? I think the people who matter include politicians, civil servants, and the opinion formers, the people who write in newspapers and the people who speak on TV and who people trust and believe. So we need to find a way to influence all of those people. And when I wrote the book, I was hoping that some of them might read the book, so that's one way to try and help. And people who have read it have said to me, oh, they are very glad that they read it. And some people have said, I wish I had read this 1 year ago when I started my job as a minister. So that's one way. But these are very busy people, and it's very difficult to get their time. So if you get half an hour with a politician, you are lucky. So it's difficult. Another way we have tried to help with this communication issue is through the 2050 calculator tool that I showed you earlier. So, is it here? No? Yes. So this tool is intended for the general public, for opinion formers, for civil servants, and for politicians. And when I get time with politicians, for me, a high priority is to ask if they would like to use this tool and see what messages they get from it. We have very recently started using this tool for engagement with the MPs in the UK. So the tool has been published for about 2.5 years now, and we've just started trying to spend time with politicians to see if it helps them change their minds, to help justify opinions. We are also trying this with the general public, so we are intending to run sessions where a group of people are given the tool and are asked to agree with each other on a pathway, a way of meeting our goals for 2050. And the hypothesis, which we will test, is that interaction will change people's minds. That's what we hope will happen. I'm not sure, but that's why we're doing it. We're hoping that people may change their opinions about other people's opinions.
Yes, there's one metric that you haven't mentioned. Of course, it's not purely physical, but I wonder if you'd want to comment on energy intensity of wealth production or carbon intensity of wealth production, because there you see some amazing contrast. The U.S. just being at the world average, and the countries that need the most to develop is spending about twice as much to produce their wealth.
Okay, so the question is about carbon intensity measured per unit of gross domestic product, or per unit of economic activity. And what do I think about that metric, and maybe why did I not mention it? Some people, when they talk on this topic, write down what is called the Kaya identity, where you say emissions are equal to something times something times something times something, and one of the somethings is a carbon intensity of the economy. That is an identity that brings money into the definition of carbon emissions, and I feel reluctant to do that. I don't want to have money in there, or GDP, because I don't really understand money, and I don't understand economics, and I don't understand GDP, and I am suspicious when we say, oh yes, the GDP of this country is this much, and this one is this much, USA, China. Well, doesn't it depend on the exchange rate? And isn't the exchange rate perhaps somewhat arbitrary? So I don't really believe in GDP, and I don't want to mess up the nice physics equations by including something that has money in it. I think the physics is the physics. People emit carbon because they want to get into a little box and move really fast in the box, and that makes swirling air behind them. And it didn't have anything to do with GDP. They got the fossil fuel and they burnt it. And we don't need to have economics to explain what happened. So I don't look very much at those numbers, but I agree they are interesting.
Thank you.
My question is about the general public awareness on all these things. And I've seen in the news, on the TV or on the papers, more and more communications about greening our way of life, or greening our way of producing energy. And my impression is that most of the time it's just greenwashing. It's not really solutions, it's typically than your partner and things like that.
Yeah.
And don't you think that people that count or politicians could act on the mass media in order to just forbid stupid communications that mislead the people into thinking that they will act good if they...
Yes. So the suggestion is, shouldn't politicians pass a law that forbids stupid communications? That it's possible that might be a challenge for some politicians. But the point is that some communications are greenwash. Many organizations will say, oh, here are 7 things you can do to make a difference, and they have a list of 7 things, and maybe 1 or 2 of them are good ideas, but maybe several of them are irrelevant, they're silly, and the list doesn't include fly less. If it has a thermostat, it'll say, turn the thermostat down to 19, when it should say, turn it down to 13. So, yes, there's a real issue with these lists. And my suggestion would be, if you see a list in a newspaper or somewhere, write to them and say, no, there is a free book, and the free book that anyone can read says that these are not the most important 7 things, here are the numbers. And hopefully, if enough people do that, if enough people point out the greenwash, maybe we can improve the quality of the public discussion. But it is always difficult, because there are people who want to mislead you. For example, if they have a company that wants to sell something, they'll say, oh, this is wonderful, it's green, it is fluffy, it's super. And so they will be misleading. And also, people just get confused, they don't understand units, they mix up kilowatts and kilowatt hours. So it's always a difficult battle. But if everyone gets involved, especially the physicists and engineers, I'm sure we can make some progress.
Related to this question, because mainly with respect to fossil fuels differences, there is, my feeling is that we have been relying almost entirely on the CO2 message for the last 10 years or something, and the resource constraint and finite resource aspect is almost never there in the media. And so it somehow provides a false message on the urgency of the thing. If you compare to the 70s, we are in an oil shock, and nobody is saying we are in an oil shock, basically. So, in a way, the CO2 message is a bit easier, because we can say we can keep on doing the same and make it cleaner, whereas the resource constraint message or people message is at the same time simpler to understand for people, but it's almost not there. Whereas if you compare in the 70s, the CO2 message was not there, but oil is getting more expensive, was really there. So just your view on this, my feeling is that we rely too much on the CO2 message to more or less cover up the true urgency of the resource aspect.
Okay, so this is a question about how much we should emphasize the different motivations I mentioned at the beginning. So there's the total resource scarcity for the world question, or the local resource scarcity and security of supply issue, not wanting to depend on oil from Arabs or that sort of argument. So these are motivations, and the climate motivation is in the middle. How much should we emphasize these different arguments? Well, my tactic is to respond to the audience, really. So if it's an audience that cares about security of supply, then I talk to them more about security of supply. But the argument about oil security and fossil fuel security and the total resource, I think is a little bit of a shaky foundation. You're right that many people respond to that, and they will say, yes, I want to reduce my dependence on oil because oil prices are high and they may go higher, and gas prices are high in some parts of the world. So that's a useful argument, but actually political decisions could transform that tomorrow. So Saudi Arabia could produce more oil, and then for 3 years the oil price would be low again, and then it would go up again. And so it's an unreliable foundation. So I agree, we do need to emphasize all of these arguments, and I think the truth about fossil fuel prices is they will be volatile in the future. I don't think we can definitely say that the prices will always be high. I made a bet with someone, and the price was above $100 per barrel, that it would be a long time before it went below $100 per barrel, and I lost that bet because it went back down to 60. But they will be volatile. The fossil fuel prices will be volatile because it's difficult to mobilize the infrastructure very rapidly. So there will be times when we have oil shortages and gas shortages. So maybe that is an intellectually sound way to worry people. The fact is the oil and gas community are very good at coming up with new ways of reducing costs. So shale gas is being produced in various places. And so I think the prices of fossil fuels could remain similar to today's prices for quite a long time, but they will be volatile around that average.
But it is not,
yeah. Question wrap up.
Excusez-moi, il faut qu'on s'en aille quand même dans quelques dizaines de minutes maintenant. Donc je vous demandais d'intervenir rapidement, je prends encore quelques questions et après on arrêtera.
Thank you very much for your brilliant talk. I really enjoyed the idea of the online calculator. I mean, this model that is available on the internet for everybody. For me, the question is more about how you aggregate preferences and diverse preferences for different trajectories in the energy transition. You may know that today in France was held the second session of the French Council for the Energy Transition, which combines different stakeholders, so from representatives of the industry, of the trade unions, of the politicians, and of the different regions, which is to produce an energy transition law by next September. So my question was, what would be your advice for this experiment in France, which is a complex mixture of expertise and politics? Thank you.
Okay, so it's a question about preferences and how to find out people's preferences and how to take them into account. One thing I would say is I think it's important not to do an economic optimization. It is traditional in the energy economics world and in government to make policies on the basis of software that does economic optimization. So the question is, what is the lowest cost path to the 2050 target for Europe or for the UK or for France? What's the lowest cost? And if you do that, you have completely ignored people's preferences. You've just turned them into a market model. And one thing I like about the 2050 calculator approach is it does not do that optimization. It leaves it up to the user to include their own preferences, and cost information is one of the pieces of information, but they can include their own preferences also. And it is still based on physics. So the advice I would have for France, if you were asking for my advice, is I would say make sure that it's based on physics. Make sure that people are not allowed to express any preference until they have understood the physics and have got a plan that adds up. So you need a calculator for France very quickly, because people need to be able to express preferences in a way that does add up. Because I'm sure if you don't have that calculator, most people will have preferences that do not add up. In Britain, we have people who say, nuclear is the answer, look at France. And they don't realize that France gets almost all its electricity from nuclear, great. But that's only the electricity, and you still have transport and heating, which have not been solved. So that's smart people who say, yes, nuclear is the answer, but they haven't thought about the whole system. So I think you need a calculator, and the calculator can then be a useful tool for helping find out people's preferences.
So I'll take two more questions, then after you.
First, thank you for your talk, and I like very much the story at the beginning with the 7 kilometers of biofuels you needed along the road. But I would like to use this to compare this distance, because with the 7 kilometers compared to the width of the road, of course, you can think it's something much big. But if you go to electricity from PV along the road and with electric cars, then from your figures, you will decrease by 160, at least, maybe 300, this width, so it becomes comparable with the width on the road. So can you comment on that?
Fantastic. So the question is, what if we asked a different question? What if we said, let's use the verge of the road for solar panels to power electric cars? Then how wide does the verge need to be? And the assertion is that the width would be significantly smaller, and I agree, because the average power of solar panels is 5 watts per square meter if they're not shading each other, and the plants for this calculation they're below 0.5 watts per square meter, so it'll be at least 10 times smaller. So it could be only 700 meters wide along the side of the road. And if you switch to electric vehicles, you get another factor of 4, so maybe it's only 100 meters wide along the edge of the road. So yes, it's only 100 meters wide, and you would need somewhere to put all the batteries to fill up when the sun is shining, so that you can carry on driving in the winter. So I agree with your calculation. Yes, solar panels require much less land area than biofuels, and yes, electric vehicles are much better than today's cars. So that's exactly the sort of calculation that I like to encourage.
Yes, but this is still only 12,000 cars over 1,000 kilometers. That's not many cars.
It is.
Calculation.
Okay.
80 meters between cars is 12,000 cars over 1,000 kilometers.
Okay, so this question is, do I have the right number of cars on the road? So for this calculation, the assumption is that those cars are driving all the time, 24 hours a day, for this simple calculation. Now the truth is that cars are only driven for about 1% of the time, so there are far more cars driving only 1% of the time, and the spacing between them is also not to actually do a full calculation for the whole energy system, we need to do a different calculation, but that's what we can do with these simple methods.
Okay, I have a question about bricklaying. Can you tell us what are the objectives for your country for carbon reduction? And as you are the chief scientific advisor, do you think you will meet those objectives?
Okay, so let's make this the final question, shall we? So, what are the legal objectives of the UK government? We have got a legal target, and it's shown by this green line. So in 2050, we have a law called the Climate Change Act, which says that the emissions of the UK, measured within its own borders, must be 80% lower than the emissions in 1990, which means 2 tons per year per person. Do I think we will achieve this target? I don't know, it depends. But we have a description of policies that will get us to this goal. We've used the calculator, we have published a document, let me show you it. So 1 year ago, the government published the carbon plan, and the carbon plan looks like, how has it gone? This. So the carbon plan describes how we will achieve that goal. And one of the details of the law is every few years the government must describe what it is going to do to meet the targets, not only the 2050 target, but the interim targets every 5 years. So this plan describes how we will meet the goal. And incidentally, this document also admits that our current policies are not sufficient to reach the goal. So this document says we need additional policies, and the document identifies the areas in which those policies should be developed. So essentially the UK has a target, it is not on track, but it knows it is not on track and is describing what it ought to do. Watch this space.
Well, there's a time to stop.